of mapping, so this becomes plus constant. So this becomes a special case that never happens. Another tractable special case is that when source distribution P of x is Gaussian and the mapping P of y condition on x is Gaussian. So for these special cases, you can calculate mutual information very easily. But in reality, things are very complex, and you should approximate it as you do. For example, in variational inference in machine learning, you approximate it because it is the distribution is highly complicated. So we use the same trick as you might have guessed, the variational lower bound on mutual information. So the equivalent formulation of x and y, mutual information between x and y, is h of x minus h of x condition on y. And from here, I just write h of x condition on y by log of p of x condition on y, p of x and y. And this is h of x plus p of x and y log of p of x condition on y, and then minus something and plus that. So minus from here, minus p of x and y log of q x condition on y plus p of x and y, the same thing, log of q of x condition on y. You know, this is just 0. I just added and subtracted that. And this is the trick that we always use. So it becomes h of x plus. And now you represent it, you say, oh, this is the KL divergence between p of x and y and q of x and y, x condition on y. And you know the KL divergence is positive and plus log of q of x and y. Oh, that's neuroscientist was talking with Lex, and I noticed that he used the term energy. This was very strange. And so this is just greater than h of x plus log of q of x condition on y, p of x and y. So this is the decoder. This is the decoder. Q is the decoder. So I can review that you have a source, P of X, you have encoder, and then P of Y condition on X, and then you have decoder, you get Q of X condition on Y and Z. So we have approximate that. Z is just the auxiliary variable. So I tilde of x and y is h of x plus log of q of x condition on y, p of x and y. So this is how we approximated an intractable mutual information. I tilde x and y is h of x plus log of q x condition on y, p of x and y. So we choose a class of variational distribution, q of x and y in q, such that this energy term is tractable. And then use a recursive procedure for maximizing I tilde x and y. So first step is that for fixed q, x, and y, we find theta nu. By the way, theta is just a parameter of p of y condition of x and theta. Theta nu is argmax of I tilde of x and y. And in the second step, which pushes up the lower bound, for just fixed theta, we calculate q nu of x condition on y, which is the argmax of I tilde of x and y, q, x, and y in your chosen class of distribution. And that's it. Next weekend, I will be talking about a very important paper called MINE, Mutual Information Neural Estimation, by an amazing researcher, Aaron Kurzweil. He is also the founder of GANs, by the way, and he works in Mila and CIFAR. So why is this article very important for me? Because we want to know what is the mutual information between X and Z. So it's another representation. We have Z, we have X, we have encoder. For example, another representation is when you do contrastive learning. That article, SimCLR of Geoffrey Hinton, that he used two augmentations, and then for each augmentation he used a representation, and he introduced a loss between them, SimCLR similarity of two positive samples, and you want to reduce this loss. So that SimCLR paper was another presentation, and but here we don't do any augmentation. So X is just one of them. We don't crop the image, or we don't zoom or translate or anything. We don't do anything. We just want to maximize mutual information between X and Z. And and this is important because we can apply MINE, this algorithm, to improve adversarially trained generative models. And we can implement information bottleneck. Of course, I will explain what is information bottleneck in future. And we can apply to supervised classification. Another application is just feature selection. You select the features that might be relevant. In explainable AI, all of these attributes are important. But here, we use a mutual information is our measure. We want to maximize it. That correlation plays an important role in machine learning, especially financial markets. Everything is correlation because they care about linear statistical dependencies between variables. But mutual information is the nonlinear version of that. So it's nonlinear generalization of that statistical dependency between variables. But historically, this mutual information is difficult to compute. Of course, it's a measure of true dependence, but it is tractable for discrete variables, because if it is discrete variable, you can use the sum, for example, can be computed exactly. So no problem to calculate mutual information. But in general, mutual information is intractable. There are many old approaches. One of them is likelihood ratio estimators based on support vector machine. The other one is non-parametric kernel density estimator. The other approach is binning, but they do not scale well with the sample size or dimension. And so I of x and z can be written as h of x minus h of x condition on z. And this is just the KL divergence between P of xz and P of x, P of z. When the KL divergence between the joint and product of marginals. So the larger this KL divergence, the stronger the dependence between x and z. And so next week I will explain this mine article. But now I want to say that the future in 2031, many articles are about Fourier transform and wavelet transform applications in machine learning. For example, if you have a neural networks, at least your input could be represented by the Fourier coefficients or wavelet coefficients, wavelet transform coefficients. Because, I always think like this. You have a picture of a face here. You don't need all of the pixels, for example, 1 megapixel. You don't need 1 megapixel features. You don't need those high-dimensional feature space to understand a picture, a dog, a cat, a face. You don't need that. Because if you represent it by wavelet transform, everything becomes simplified. So maybe after 2 or 3 level approximation of discrete wavelet transform, you can represent your signal. You don't need, for example, 1,000 features to represent that. And human mind is like that. Human mind, for example, the problem I have with the sparse coding, neuroscientists say that sparse coding is implemented inside our brains. But I say that our brain does not do ISTA, does not know the concept of lasso, does not minimize, the L1 norm. What our brain can do is just say that, okay, a bunch of neurons can understand some concepts like face of dog and cat and human. A bunch of neurons can understand car. And we don't need any optimization like L1 minimization to do that, because if the coefficients of wavelet transform has highest similarity with the coefficients that is done inside your brain, then your part of your brain understands that this is a face that I know, for example, or this is a wheel of a car. So it's like a projection onto different Hilbert spaces. In each Hilbert space can recognize one concept. That's why, for example, when you rotate an image, for example, in MNIST we have 2, for example. If you rotate that, it becomes like this. But the nature of this, or if you zoom or if you crop or anything, the nature of 2, or even you thicken this 2, the nature of this is not changed. It is still 2. The label 2. So you should notice that what happens to the wavelet transform of that. You will notice that some of the coefficients are fixed, but so this is the main information because most of them are fixed, and then we have a little bit perturbation. Some parameters, some coefficients do not agree with each other, and this is the way to encode information of pictures or concepts or anything inside your brain. And that's why abstract harmonic analysis, which is doing, for example, Fourier transform on groups, on Heisenberg group, for example, which is a non-commutative, and it is not abelian. So abstract harmonic analysis is important. And some people do it computationally, and they created a field that is called computational harmonic analysis. And I want to introduce an amazing scholar called Rizi Kondor. He introduced several ideas about Fourier space neural network, and if you read his thesis, you will understand how you can represent. First you should understand that for any group element G, you have a representation. So from group to GL. So this is the representation theory. So mathematicians do representations much more efficiently than machine learning engineers, because they use discrete spaces, they use discrete math. They don't, so they represent spaces. So they work on discrete mathematics and discrete objects. It is more efficient because these discrete objects can represent information. For example, if you see a picture of your friend's face, you don't need infinite level details of the face to recognize that this is image of your friend's face. Just 2-level or 3-level approximation of that is enough for your brain to understand that. So signal processing engineers are more successful in representing data than machine learning engineers, because they respect that data should be represented as an element in function space. So this is what mathematicians or some signal processing engineers do. But unfortunately, machine learning engineers, deep learning engineers, they just put their input inside the neural networks. They don't do any pre-processing. I don't say the kind of pre-processing that they create sparse code and then they give it to the next levels, the downstream tasks. From the beginning, you can do this pre-processing and represent your data in a much less dimensional space than the original high dimensional. So